to begin. So I've got a beam 10 metres long. I've labelled it where the event takes place. I've got the beginning, then I've got one for first reaction, first support. Then I've got C for the 30 kilonewtons pushing down. Then I've got my distributed load, obviously. Then I've got my point D there for my reaction there, and then where it stops. So I'm going to use those as my reference points. So first thing we need to do is find out what our reactions are here. This reaction, we'll call it RB and RD. So moments, morning. Moments about RD I'll do first. And find what RB is, our first one.
Is that RD or RB?
That's RD.
Finding RB.
No, it's a bit small that from the back. RD. So I'm going to use this as a moment there, about that point there. Then I'll find what RB is from that. So clockwise equals counterclockwise or anti-clockwise, like this. So what I've got pushing it clockwise, if it's held there, then the only thing I've got pushing it to, so it's held there, so pushing it clockwise I've only got this one. So I've got RB, and that's 6 metres away. So 6 metres away, and that's going to be, I've got, let's use my notes so I don't go wrong. 30 times 4, so that's that one, that's 4 metres away. If you work that out, and I've got 280 times 3 for that one. So my distributed load is 28 times 10, it's working in the centre from the averaging point of view.
What have you times 3?
It's 3 metres for this point. So I've made the distributed load into like a point force, acting in the middle at 5 metres, so it's 2 metres from there, the middle's 5 feet, so it's 3. Bless you. Actually doesn't sound good on the video. So, if I rearrange this, I will get RB to be 120, all of those, plus 840 divided by 6, which gives me 160 kilonewtons. Okay. Now I could cheat, take all my forces down, take that away from them, and that will give me up, but it's best to do it again, and then I can test my answer at the end. So I'm not making, if I've made one error, I don't make 2. And then I can also check that my answer's correct at the end as well, as we'll see when we do a test. So if I do my moments, so moments about B, so that's B this time. So this time I'm going to have, so it's held here, so pushing it clockwise, if it's held there, I've got these two, and the only thing pushing it counterclockwise is that one. So I will get 30 times 2 plus 280 times 3 equals 6 RD. Okay? So if I rearrange that, I'm going to get RD, that should be a small d, but not that it matters. 6 RD equals 60 plus 840 divided by 6 equals 150 kilonewtons. So RD is 150 kilonewtons and RB reaction is 160 kilonewtons, and I'm going to label that. You alright, Jake? Yeah. Right. So I'm going to label that so I can rub this out because we're going to need a lot of space. So this one, RB is 160. I won't put the units in because there's not a lot of space. And this one, RD, is 150. 150 kilonewtons. Okay, so I think I've got everything labelled I need. I need to clear this off. Okay, to black. So now we're going to find a shear. We're going to do a shear graph. So we're going to find all our measurements for the shear graph. So before A, so I've labelled all the events. So A is where it starts. B is where we've got the reaction acting on it. The distributed load we can't treat it as an event because it's happening all the way along. So it'd be like infinite amount of events. And then we've got this one down, and then we've got reaction D, and then we've got where it ends. So I've labelled them A, B, C, and D. Neat. Nothing clever about that. So before A, there's nothing happening. There's no shear force on it. Then we've got from A to B. At that point, we've then got a distributed load starting to happen. So we've got there minus 28 times 2, which equals minus 56. Then when we get to B, we've got at B we have minus 56 where we started, and then we've got plus 160 for this, 160, which gives me 104. We've gone back to positive. Then from B to C, we're now in this realm. From B to C we have 104 plus negative 28 times 2 of those. That two there basically. And that gives me 48. And then when we get to C, so at C, we've got a new thing happening. We've got this 30 kilonewtons. So that's pushing down, so it's a negative. Everything down is negative, everything up is positive. So we've now got, starting with 48, and then we've got minus 30, which gives me 18. And then from C to D, so that's from there to there, we're going to have a distributed load again, and that's going to be starting at 18, and then it's going to be negative 28 times 4, which will give me minus 94. And then at D itself, at D we have minus 94, the starting point, plus 150, and that gives me 56. And then from D to E, that's from there to there, we've got 2 meters of, so we start at 56, this is a plus 56, and then we add to that a negative 28 times 2, which obviously is 56. So I'm going to get back to 0. We should always end up back at 0. So I can say at E as well. I'm going to have 0.
We just run through that again whilst we're not copying it.
Certainly, yeah. So we've put it into sections. So before we get to A, before we get to the B, nothing's happening. There's no force on it, nothing's happening.
Yeah.
So it's simply 0. When we travel from A to B, we've got a distributed force for every metre, 28 kilonewtons per every metre. And with 2 of them, it's a negative because it's pushing down. So it's minus 28 times 2, and that's giving me the minus 56. At the next point then, we're starting at a minus 56. but then we've got 160 pushing up, so we add 160 to that negative, making it 104. And then it just progresses the same. So then with 104, we add to that this next distributed load up to this point, which is 2 times minus 28, 2 of those, takes me to 48. At C, we then have a negative value pushing down, a point load, 30 kilonewtons.
Yeah.
So that takes me down to 18. Then from C to D, we have another distributed load, and there's 3 metres of it this time, 4 metres of it this time. So that's starting at 18, adding to that, should really write it like this. Adding to that negative 28 times 4 takes me to minus 94. And then I've got at D, I've got a positive force pushing up my reaction of D of 150.
Yeah.
That takes me to 56. And then finally, my last 2 metres of length are a negative 56, added to me 56 gives me 0.
Yeah, I understand.
So when I get to 0, E, I'm back at 0.
That's alright.
So that's what we hoped for. Right, so if I plot that, and I'm going to do a rough sketch on the board, obviously you do this on graph paper. If I do a rough sketch, best I can. Let's make that a little bit better than that. You think I'd get a ruler out, wouldn't you? It'd be too easy. So, this is divided into 10. That'd be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But where you've got them labelled, so this is A, this would be my B, then we have my C, and then my D would be here, and then my E. Okay. And then it goes up to the maximum up is 104. So I'm going to need to swash my scale a little bit on this. So for example, let's say 100's there. It's going to be 50, and then we go down to minus 94. So it's sort of the same kind of scale on this one. Obviously this is just a rough guide. On graph paper it's going to be a lot more precise. So I've got here, it starts at 0, at A, then it goes, when I get to B, well we get, from travelling to B we go to 56, minus 56. So I'm going to be roughly here. And then it goes, it gets a boost up to 104, so that's going to be somewhere like there kind of thing in my rough sketch.
Is that at C?
No, that's B.
That's still big, oh yeah.
Yeah. So it's that boost it gets, it takes it up to 104. And then we go back down again to at C, we're going down.
So, sir, shouldn't your first dot be in between? No, in between A to B.
I could actually do it that way if I did 20, if I went from, if I put B there and labelled as C for example, so I did it by the metre.
Oh.
I could do it by the metre and I'd actually then get one in the middle like that.
Okay.
So it wouldn't really gain me anything, I'd just be doing more work because it's a straight line from there to there.
Yeah, okay.
It didn't come out too bad. And then it's a shear, very literally shear, line straight up to there, to where that dot is, honest. Where that dot is there. Okay? And then we're going down at a C, so here we're going down to from B to C to 48, so it's just around the 50 mark. So it goes like that. And then we've got another straight down point at C of that 30, so that takes it down to 18, somewhere roughly there, so down to there. Then it continues, so the gradient, because it's a distributed load, that slope is always going to be the same steepness, the same gradient. That one, this one, which then goes to that minus,
94. Is that a D?
yeah, where am I? I'm here, 18, yeah, minus 94, so it's going to be, and that's at D, so this is going to be really rough and ready, 94, something like that-ish. See if I can join that up. Okay, that's supposed to be the same slope as that, but we'll ignore that. And then it gets this boost of 150, which takes up to 56. So we're back up here now. So up it goes to there. Then finally, it goes down to 0. So we've got to 56 at this point, then down to 0, so to here. And again, that should be the same gradient. And it will be on your graph paper. I don't know if you can see that, but that's my version. A lot neater than that. So it shows you, comments on it really, it shows you that the biggest area it's likely to shear is on this point here, 2 metres. Because that's where you've got the biggest amount of force in a short space of time, shortest change.
Will we have to write that?
You could comment on it, yeah. And this would be your next point.
What do you call it? The biggest shear point?
Yeah, because you've got your least amount of change in that distance there. So you've got this pushing it down and this pushing it up, so it's likely to go there. But it depends on the material, what it'll do. If it was quite malleable, it might bend here, bend along that length and not even shear. It's a shear point really, depends how strong the material is. So obviously when you're building something, if you're doing a building, you want the material to be able to take that force anyway. That's what the object of the exercise is for it to actually not shear or bend. Okay? So it's going to be your most likely point. And then this will be your next most likely point.
Can you just move a bit for a second, please?
Yes, I can do that.
No.
And then when you've got that down, what we'll need to make a note of before I rub this out is this point here. So that one is where it crosses, it's roughly 4.7 off my graph paper, not off this really. Though it looks like 4.7 on here as well. 4.7. So remember that, I'm going to write that up here. Because we're going to need that, that's going to be our maximum bending moment when we do the bending moments graph.
Why are we taking that point?
That's what will give us, remember when we showed on the previous example where we had missing data?
Oh yeah.
And we had to either guess, but we didn't have to guess because we just used that. That's our maximum bending moment where that crosses 0. So there.
Right.
So we'll use that when we do our bending moments graph.
So why didn't you pick 2 or 8? They also.
So the question was, why is it there and not these points here that I use for my maximum bending moment? Well, they are maximum bending moments as well, but when I actually plot it, when I actually do the plot, it's going to be, do a little sketch. It's not going to be, this is a very little sketch, it's going to be like this kind of shape. That actually goes to 0 actually there, like that. So that's a little bit wrong. So it has actually got it's the minimum there. It's a turning point in the shape of it. But we actually have the data there, don't we? But what we don't have is we don't have this data between a couple of points here, between 4 and 5. So it's going to be 4.7. And why it's crossing that line is because that's where the gradient changes. So here it's going positive pushing up, and here it's negative pushing down. So you've got that shape Okay, and it's that middle bit where it stops doing that, basically, where it's got a 0 turning point. Okay, we've obviously got a 0 turning point there and there, which is these bits. Okay, that makes sense? So now for the bending moments graph. So it's worth doing yourself a little line graph. Doesn't have to be anything, doesn't have to be anything posh. Just for labelling purposes, 0.
Well, I can't hold it. I've just got to get a second word.
So that'd be 10. Okay, so that's my, just a nice little sketch so that I've got a feel for where everything is. So here I've got 160 up. And here I've got down 30. And here I've got 150. So it gives me a feel for doing the bending moment. So what we're doing with this is we're working away from left to right. So when I hold it at 0, imagine it's held at 0, what's the, and then I'm working to the left to see what's going to bend it. Well, at 0, nothing's going to bend it to the left because there's nothing there, there's nothing acting on it. So when x is 0, then it's going to be, is that the best way to label it? Probably. The bending moment will equal 0. Okay. Maybe I should have done this on the left side of the board instead of the right, but never mind. X equals 1. The bending moment there is going to be, let me write this in, then I'll do the next one and then I'll explain because it's easier to explain on x equals 2 than it is on x equals 1.
Should we keep copying it?
Yeah, so let me just put this in and then I'll explain what I've done on the next one, which will make more sense when I get there. I've got here minus 28 times 1, it's all divided by 2. So if I do the next line, the bending moment of the next one is minus 28 times 2 divided by 2. That gives me those answers, by the way. That would be minus 14 and that one will be minus 56.
Doesn't the third one supposed to be x2?
So, yes, it is, yeah. Just testing. Right, x2. So what it means, what's actually happened, if we go to this one, it's a bit easier to follow. So the beam's been held at 2 metres, so it's sort of solid, and what's acting on it, what's trying to bend it? Well, you've got the distributed load only at that point. This 160 doesn't make any difference because that's pushing on it. It's not bending it. You can't have a bending moment if you're pushing on the point. Like, remember the hinge, if you push on the hinge, it doesn't bend. It tries to shear it, if anything, but it doesn't bend it. You've got to move away from the hinge to make the door move, bend, if you like. So we've got to, so that doesn't affect it. So it's only these 2 metres of distributed load. So that's what this is. We've got minus 28 because it's 28 per metre pushing down. So it's negative because it's pushing down. 2 of them, so 2 because you've got 2 metres of it. And then this is your bending moment, 2. And then it's the average of that 2. So remember when we did the uniformly distributed load and we said it works in the centre, it's half the distance and it works out, it averages it out, and you can do the maths if you want and work it all out, but you just end up getting back to this. And then remember we said you could do it by the centimetre if you wanted, but you'd still end up with the same result at the end of the day. When we put this on the graph, this will be a curve, it's end up being a curve. So it's going to be times your bending distance averaged out to 2, so you divide by 2. Average is always divided by 2 in this situation. So that's where it's come from. So that's why that's divided by 2.
Makes sense.
Okay? Because it's going to be times a half, basically. Right, so x equals 3. So it's same kind of stuff as before. Right, let me just work my way along. X equals 3, I'm going to have minus 28. So this number is going to keep increasing. 1, 2, 3, times 3 halves, because you're dividing it by 2 to get that average. And this time we've got plus the 160 does make a difference, because we're now 1 metre away from it, so we've got 160 times 1 basically. I won't write the times 1 in. So that should be equal there. I'm going to move these over here, because we're working our way along and we're going to use a lot of this board space. And that will give me 34. Okay? And then x equals 4. So it's same thing's happening. We're moving along a metres every time, so these numbers are going to change by 1 every time. The amount of them has gone up by 1 and the distance has gone up by 1. So we get minus 28 times 4 times 4 halves. Obviously you can cancel this down as you do it if you wish. Plus 160, and this is now 2 metres away. And that gives me 96. And then at x equals 5, I've now got bending moment is equal to minus 28 times 5 times 5 over 2 plus 160 times 3. We need to keep looking to see nothing else has happened. We're at 5, so we're here now. At 4, nothing changed because there was 30 acting on it, but it wasn't bending it because it was acting.
Why are you changing it by 3, Kevin?
Because it's 3 metres now, is that 160 away from here?
From that, okay.
Yeah, so that's the bending moment of it. And then we've got, this time we've got the 30. So that's plus, it's acting down, so it's a minus 30 times 1, which I'm not going to write in again. Again, I'm not going to write in, shall I say. Which takes me to 100. You might think that it's going to jump by 30 or something, or go down by 30, but it's not, because everything's changing. Every value is changing every time. Okay, so next one. So same again, exactly the same process. Minus 28 times 6 times 6 divided by 2 plus 160 times 4 this time plus minus 30 times 2 this time. Anything else happen? No. Equals, so x6 gives me plus 76. And then x of 7, bending moment is minus 28. It's starting to get a bit tedious, this, isn't it? Let's keep that level at least. We haven't got a lot of space. 28 times 7 times 7 halves plus 160 times 5 plus minus 30 times 3 equals 24. Then x is equal to 8. So again, whoops, 8 times 8 halves plus 160 times 6 plus, if I go wrong just shout at me, minus 30 times 4 equals minus 56.
What stage put 150 in, Kevin?
After second support, so on that.
Right, we're there now.
Put it on the 9.
Yeah, because it's not acting, it's pushing on it at the minute,
Yeah.
so it's not got any bending moments.
It
So
will
it's
be-
going to occur next.
It's equal to that support force times 0.
Hopefully I'll fit all this in. Yeah, that's the other issue. So 9 minus 28 times 9 halves plus 160 times 7 plus minus 30 times 5 plus that 160, which is a positive because it's
50.
pushing. 150, sorry.
Yeah.
150 times 1, so I'll just put 150 in. And that equals minus 14. And then finally, for this, x equals 10 minus 28 times 10 times 10, 160 times 8 plus minus 30 times 6 plus 150 times 2. So it's 2 metres to 10. And that gives me, apparently, I'm pleased to announce, 0. So we've got everything we need for the graph. I'm going to return to that maximum bending moment in a second. Doing a quick sketch, rough sketch of the graph. So you've got to look at your max values. Max is 100 that we've got here. We know that the max bending moment is going to be a bit greater than that, because it's a 4.7, so it's just going to be it's going to be between them two. The minimum is minus 56. So in this case, my graph would be something along these lines. Very rough and ready sketch. 50, 100, minus 50. Okay, doing a different colour. So it goes, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at 2 here it goes down to minus 56, is it? Yeah. And that's a curve, because it's a distributed load. So on these you always get a curve where the distributed load is. That's exactly what would happen when you were bending something like that. It would bend, unless it's sheared, of course. So it bends down to that. Then it goes up to, you'd have to plot all these points obviously, but just doing a quick rough sketch at 3, what have we got at 3? We've got 34. We'll up here somewhere. 1, 2, 3. So this is also strange bend. And then we've got at 4, we've got 96. Somewhere like that. And then at 5 I've got 100. 1, 2, 3, 4, 5. It's a little bit higher. And then we've got a minus 56 at 8, is it? Yeah, at 8. So basically, roughly sketched, it's going not like that. Shall we try again? Something like that. And then we've got, after the, sorry, this is the bit that's missing, 4 and 5. That bit we don't know. And then we've got 76, somewhere around here. So, a few dots missing. It goes down, whoops, that's terrible. It goes down like that, if I could draw, and then it goes back up to 0, that, in that kind of shape. And we're missing data somewhere between these two, 4.7. So we need to do that max bending moment stuff, which is 4.7. 4.7. So we've got this time, we've got minus 28. So we're working from this point here, there. And we're doing all the calculations from that point looking to the left, just like we did before. So we've got minus 28 times 4.7, because 4.7 is looking to that point, times 4.7 divided by 2, plus 160 times 2.7 minus, I haven't got enough space, so I'll go under here, 30, sorry, that's like that, plus 30 times 0.7, so it's not even a metre away, and that equals 101.74 kilonewtons. Put the units in. So that's going to be, back to blue, that's going to be somewhere up here. 101, it's not far away, is it really? There. So actually, in this particular case, doesn't much change the shape really. But in some, it might do. As we saw in that previous example, it was quite a big step, wasn't it? That we're missing. So if I'd just gone straight across, it would have stopped at 100. So it'd cut the top off of the shape really. So that gives me the 3 points where it wants to bend most. But this is obviously the one where it's most in the middle. Not surprising because you've got this 30 kilonewtons pushing down in the middle as well as a distributed load. So it's trying to bend it in the middle. So you'd have to turn this the other way up really. Well, mirror flip it across to get the actual sort of how it's trying to bend. Because obviously we've got pushing up as a positive, but it's pushing down that we think of as bending. So it's the other thing to note is that no bending takes place where it crosses a zero there and there. No bending takes place, and they're known as contraflexures. Flexure. So it don't flex, in other words. There's the on the graph. I've shown the next one. Where is the contraflexure? So it is there. So those 2 points are called contraflexure. Now you can see that at the back. Contraflexure. Okay. And that is it. That would be it, the complete bit. So the graph helps you get a feel for what's actually happening. You can see a lot of when you look at the original point, alone the intelligence gives us a feel of what will happen. You know, if you're pushing up there, that's the bit that's not going to bend down, and it's going to bend in the longer lengths more so, and it's going to try and shear the shorter distances, just like a pair of scissors. There's a short distance between the two blades, so that's where you get your shear.